Good day, ladies and gentlemen. My name is Ian Jones. I'm a geophysical advisor with ION GX Technology based in London, and my background is to specialize in imaging and model building. And today's talk is going to be on near-surface effects for depth migration. Specifically, we're going to be looking at how you handle the near surface, because as we all know, if we're working in imaging, the near surface is the main problem we have to deal with before we get down to the target level. So I'll be looking at a bunch of different technologies and techniques for resolving near-surface velocity anomalies. So most of these techniques are approximate, none of them are exact, but from a pragmatic point of view, I'll review the different techniques we have available to us today. Now we all know that one of the biggest challenges we have is near-surface anomalies, and unless you can resolve them, your ability to image the deeper structure is going to be compromised, simply because waves pass through the near surface on their way down, then they reflect and come back through the near surface on the way to the receivers. So they get hit twice by near-surface anomalies. So if you don't deal with them, you're in trouble. Now, one of the first things we like to do, trying to understand the problem, is to model it so we understand a bit of the complexity involved, and also we can test algorithms and how those algorithms respond to synthetic data, knowing what the right answer should be. So let's have a look at some near-surface modeling. So in this case, it's a very simple modeling. There's a deep structure which is more or less flat, and at seabed, which you can see there, there's a very small velocity anomaly circled there. So this is a deep, narrow anomaly with a velocity contrast in comparison with the neighboring sediments. So we'll have a look at its response. So we model these things with an offset of maybe 5 kilometers, whatever. This isn't really important, the parameters we're using. They just have to be representative of the type of data we use in our seismic acquisition in reality. So what does the data look like? There's an example of manual picked velocities to flatten gathers, and then just looking at a 50-meter offset plane. So in this case, you see the push down below the channel and the effect of the channel manifest itself on this near offset. So this isn't migrated or imaging, it's just the raw data. Now, if we look at a gather centered in that channel, this is CMP 2442, you sort of see what you expect. The near traces for a CMP in that location are affected by the channel, but the far traces aren't. So in that case, for the 50-meter offset plane indicated by that yellow vertical line in the gather, we see the manifestation of the pushdown. Conversely, if we go out to a greater offset, just over 1 kilometer, now effectively the source and receivers are undershooting that near surface channel, so they don't see it. So the gather taken through that location and indicated at the offset of 1 kilometer doesn't see it. But interestingly, if you look down at the target level now, on either side of the yellow line, you see an imprint of the near surface channel. So on the further offsets, the imprint is not below the object creating the problem, but on either side of it. And as you go to further and further offsets, that distortion spreads out. It's roughly separated by the cable length on either side, symmetrically on either side of the position. So why is that? It's simply because a source and a receiver are affected by the channel if the source or receiver has any ray path that goes through it. So in that case, for the far offsets at 3550, you see that we have that channel manifesting itself as a distortion in the deep structure on either side of the central position, plus or minus half a cable length. So that's what we expect. And this has a consequence going through to stacking, and it's very difficult to predict in advance where this will manifest itself in a final stack. It might be that the distortion manifests itself on the near traces, or it might manifest on the far predominantly. So in the final image, this kind of distortion might lie under the channel, or it might lie to either side of it with a symmetric distortion. So it's not obvious where the distortion will lie. So let's follow through now to migration. There's a Kirchhoff depth migration just showing the 50-meter offset plane, but with the correct velocity model. And now what you see is that the deep structure is not distorted. So in other words, if we know the velocity model, we can compensate for ray path distortion and deal with it. If we don't know the velocities, we get distortion. So there's the migration now for this same 50-meter offset plane, but with a smooth velocity model. In other words, this would be the starting point in an industrial process. We don't know that the anomaly is there. Looking at migrated gathers now, it's a similar story to the NMO pictures. We got a stack there, but in the stack, we don't see an anomaly directly below where the feature was. We see something symmetrically either side of it. So in this case, the stack response is being dominated by the further offsets, giving a distortion distributed on either side of the anomaly. So it would be a bit misleading because you wouldn't see the effects below where the channel is, but off to either side of it. Now these things will be distributed symmetrically underneath the channel. Unless the geology is dipping or you've got compaction gradients, then they might be offset either way a bit. Looking in a bit more detail now, this is the 200-meter offset plane with a smooth model. And again, you see the nature of the channel and the pull down associated with it. So it's manifest more on the near offsets in that gather. Moving to larger offsets again, and in more detail, you see the nature of the distortion, and more or less it's distributed symmetrically on either side of a point directly below the channel. Not quite in this case because the geology is dipping a little bit, as would be the case for real data. A consequence of this is a corollary you can draw from this, in that if you migrate with the correct model, the real depth structure, with a time migration algorithm, you can never get the right answer, simply because a time migration will deal with all ray paths for that CMP centered on the channel with a velocity at that location. And in the real Earth velocity model, we have the low velocity in that position. However, the far ray paths in the gather don't see it. But a time migration process assumes that all traces in that gather have the same velocity, in other words, lateral invariance. So this goes on to show us that the velocity model for time migration should never be the correct model, because we'll get a better stack response from migrating these data with a model which best flattens those data, not with the real Earth model. Just a little aside, that depth migration and time migration need different models. An example of that is the following. There's a simple synthetic with constant velocities in the layers, but with layer geometries. There's a ray path impinging on that sediment layer below a near surface channel, so a seabed canyon. If we look at a time migration of that, we see something which is counterintuitive. This is migrating with the time migration algorithm with the correct velocity model. When I say correct, I mean the model that made the data in the forward modeling. And what you see there below the seabed canyon is a pull-up, not a push-down. And if you look at the gather on the side there, that's because migrating with the right model distorts the gather through time migration because it's assuming lateral invariance at the CMP location. And the far offset stack response there is dominating that stack in this case, but sometimes it might not do, giving a counterintuitive distortion. So you might think you'd have a push down, but in fact you see a pull up. So again, migrating with the right model doesn't give you the best answer for the time migration. So how do we move beyond the synthetics to real data now? So we'll have a look at the different methods we can use. They're all approximate, and we'll move towards full waveform inversion as something which should be a bit more exact. But let's just look at the different techniques we have for building near-surface models when we've got such near-surface distortions. Now, as you'll know, to build a model with current-day migration techniques, it's an iterative process. We start with an initial guess of the velocity structure. We output some depth gathers. We analyze them for residual curvature, dips of the reflectors, coherency, anisotropy parameters. They get plugged into some form of tomography, whether it's ray-based or waveform-based. And we go around a few iterations. And as often as not, there'll be at least half a dozen iterations in a complex imaging project. So it's a lengthy process. But we're never going to succeed in getting a good deep subsurface image unless we first resolve the near-surface problems. Now, I've mentioned tomography. I said it could be ray-based or wave-based. And in tomography, there are basically four possibilities. We can either work with data which is raw data as recorded, or data that's been migrated. So two classes of data, data domain or image or migrated domain data. Then we have two theories of describing how waves propagate, ray theory and wave theory. So between those two opportunities of data type and theory type, there are four and only four possibilities for solving a tomographic problem. You can work on pre-stack depth migration data with ray tomography, which is this one, or you can work on unmigrated data with waveform techniques such as the waveform inversion. And of course you can mix and match and go between those things, but underlying the tomographic systems, you only have those four possibilities. You can flip between them to constrain your result, but there's only those four possibilities overall. Now I've mentioned ray theory. Now ray theory is based on a high frequency approximation. What that's saying is that if the wavelength of sound you're using is much longer than the object you're trying to illuminate, you'll have a problem for the following reason. When the wavelengths are very, very short compared to the object, you can represent those waves with ray paths. And what you're saying there is at the interface, when the ray refracts, the behavior at this point is not dependent on the behavior on either side of it. And for a very, very high frequency wave, that is true. The vibrations of the interface here are decoupled from the interface here. But if you have long wavelengths, the vibration at this point on the interface is related to what happens nearby, namely within a couple of wavelengths. So this approximation of ray theory describing wave propagation as a refraction phenomenon, in other words, Snell's law, is valid if you have short wavelengths compared to the scale length of the anomaly. Conversely, If we go down to something looking like a boulder, which is small compared to the wavelength, so now the wavelength is longer than the object, you can no longer simply describe it as refraction at a point on that surface, because the long wavelength perturbs a large area of the surface simultaneously. So you have to move to a scattering approximation, not a refraction approximation. And this is where waveform-based tomography comes into play. So how do we set up tomographic solutions? Essentially, for the ray-based technique, you're going to auto-pick reflections you see in your data. For example, in that green trajectory, we're picking the move-out that we actually see in data. And this is an example of tomography based on unmigrated data. What you then do is take your current velocity model, ray trace through it for the acquisition geometry you have, and look at the computed travel times, and that's the blue curve. You're then going to set up a tomographic solution to minimize the difference between the observed and computed travel times in order to update the model. But there's another complexity there. Those green picks that we show are not represented by a nice smooth curve. So what you could do is do a best fit curve to those things. And if you do that, you're replacing the real detailed picks with a parametric approximation or representation. And if you feed those numbers into the tomography, it's called a parametric inversion. Conversely, if we live with the raw picks, which have more detail, that's a non-parametric inversion or a generalized move-out picker. Now, in principle, the general move-out picker will see finer detail that comes about from anomalies in the velocity field above it. So you have a better chance to resolve small-scale velocity anomalies with a generalized move-out picker. Once you go to the parametric approach, which makes the picking easier and more robust, you are limiting your resolution. So what we're setting out to do with ray theory is to minimize the difference between the observed travel times and the ray trace travel times. If we move on to waveform-based tomography, it's the same story, and more or less the tomography is the same engine, but the thing that we're minimizing is a bit different. Rather than minimizing travel times, what we're going to do is take the real observed data, then forward model it given a velocity field for VP, VS, density, Q, anisotropy, whatever, in the ideal case, make synthetic data, then subtract them and minimize those residuals rather than travel time residuals. So the statement of the problem changes a bit. We're now going to minimize the difference between the observed amplitudes on the real data and the modeled amplitudes. So that's the ideal case. However, due to limitations either in theory or compute power, we have to water that down a bit and maybe do acoustic propagation and only invert for velocity or velocity in anisotropy or whatever. The state of the art is not yet forward modeling with a real elastic wave field and inverting for all parameters. So eventually that might come, but that's not currently state of the art. So the question arises, when does ray theory fail? Now in practice, it doesn't fail when we get down to that scattering limit. That's not the main problem. So the scattering limit, remember, is when the wavelength of the sound is large compared to the object. So that's the theoretical limit. In practice, though, the things that make the ray theory methods fail is that parametric picking, in other words, not being able to get that fine detail in the move-out, the residual move-outs, but fitting it with a curve, and also the approximations we make in the numerical solutions inside the tomography. They're the two main limitations on ray theory methods. Now, if we can deal with them a bit better, we can push ray theory more towards the scattering limit, and that's where wave field methods come in. So there's a lot of mileage still to be gotten out of ray theory methods, so let's have a look at a couple of those. So moving on to ray theory versus wave theory examples, let's go through a few of those points now, looking at real data examples, how to deal with those things. First one then, it's offshore Southeast India. This is an example of ray-based tomography, and whenever you speak of tomography, you should specify a number of things. Firstly, how often you pick information, that's your auto-picking density, but more importantly, what the cell size in the tomography is for updating the velocity field. The scale length of the update is not the picking density, it's the cell size in the tomography. And often also that's not specific enough because, as I said, we iterate. We'll typically go around half a dozen times, and at each iteration you'll change the cell size. You start off typically with a large cell size, maybe a kilometer by half a kilometer, and as you iterate you close down to match the velocity resolution you have, having solved the long wavelengths, and maybe go down to 200 or 500 meters. So here's an example where the final cell size is 500, 500, 100 in the tomo. So let's have a look at that. This data is courtesy of Reliance Industries. Now the problem here is one of gas hydrates, which are a little high velocity frozen layer, trapping free gas that accumulates, so you get an overpressure zone. So the overpressure gives rise to a low velocity anomaly. And if you look deep down in the structure there, you see a push down. You also see a dimming, but that's a separate issue. That's a Q absorption effect. So there's auto-picking on a 500-500 grid for the first iteration. And if we now look at what we get with that cell size, if I flip back and forth there, if you look down in the deep, the push down has been resolved. So we've got the velocities about right. And also we can see the color change there representing the velocities that have been determined in that GeoBody, circled with the yellow circle thing there. And those velocities drop down to about 1350, 1400 meters per second. So it's a low velocity area. Perhaps it's over-pressured, hence we get a low velocity. Another example, this is now manual picking of small geobodies. It's the same data set, but a different area. And this is one where we have paleo canyons below the seabed. So you have the canyons on the seabed now, but historically in the Miocene or whatever time period it was, the seabed canyons were somewhere else. They've since been infilled with different material, so you have infilled channels. And if that infill material has a different sound speed than the neighboring country rocks, you'll get distortion in the image. And that's what we see here. So underneath those channels, the 3 channels I've marked, you see a substantial push down, and that distorts the deeper imaging. So you can't build the deeper imaging till you resolve that. So again, with an approximate technique, if we come in and pick the tops and bases of the channels, put in some trial velocities and maybe scan them with depth migration until we find an acceptable solution, this is what we see here. So that deep pull down has been mostly resolved. It's not perfect, it's an approximate method, but sometimes these approximate methods are good enough. They're a pragmatic solution to that class of problem. Another couple of classes of problem now. One where you can see channels and one where you can't see them, but you can see their imprint. So let's first have a look at a North Sea shallow water example where you can see the channel. In this case, the picking is 50-50 and the tomography smaller cell size is 300, 300, 200 meters. So you can see the near surface channel there indicated with the arrow, but you can also see a pull-up associated with it. So in this case, it's a pull-up because the fill in the channel is a high velocity material. Also importantly, if you look in the deeper structure where the velocity overlay isn't shown in color, you can see an unconformity there with an example of these symmetric distortions on either side of a point directly below the channel. So in this case, the stack response in the imaging isn't giving a distortion at target level below the channel, but symmetrically on either side of it. Not quite symmetric because there's a bit of dip on the structure. So if we now go and run a high-res tomography on that, in this case, the tomography was able to find the channel because there was enough offset visible on the gathers for the auto-picker to find. If I flip back and forth and you look at the deep structure, you see that distortion that was symmetrically distributed either side at the point below the channel has been mostly resolved. Another way of dealing with that would be to manually pick the channel. So same data, let's have a look at that. So again, there's the migration without the channel being in the model, so an early iteration, if you like, in the model building flow. And again, look at the deep structure, you see that symmetric distortion on either side of the point below the gather. And if we manually pick the event, assuming you can see it, and put in a trial velocity, maybe scan that velocity, or maybe estimate it based on the amount of pull-up you see, build a new model with a manually picked channel, again going back and forth and looking at the deep structure, you see that that distortion on either side of the channel position is more or less resolved. And this is necessary to do before we move on to trying to image the deep structure. The point being, until you've resolved the overburden, you cannot build a solid image of the deep structure. Next class, channels when they're not visible, so invisible channels. These often occur when we have very, very shallow water. In that case, for a cable of any great length, most of what you see in the shallow arrivals are not reflections but refractions. They get stacked in and look like a seabed, but they're not really. In addition, you've got the multiples in there. So what you see in the very shallow section is often refraction, contamination, and multiples. And sitting in there underneath where the real seabed might be, if there's a channel with a low velocity or high velocity fill, you don't see it. But what you might see is its imprint. So let's have a look at an example of that. So there's a migration, it's a Kirchhoff with the early starting model. You can't see the channel in this case, but you can see its imprint. You do see a channel just off to the side of the arrow there at the surface, but that's off to the side of it. That's not above that imprint. That imprint comes from a channel we can't see. So if we pick that pull down and compare it to a smooth version of the same horizon, you can build a little object, a small geobody, representing the spatial distribution of that distortion. You can then take that object, which looks like a little channel, and copy it into the model just at the seabed, then again stretch it a bit to change its shape, put in trial velocities, and see what that does. So it's a lot of manual messing around, but sometimes it works well. And this was the kind of technology that we would work with before waveform inversion came about, and it's still used quite widely. So what happens when we put in that kind of a channel object? Again, back and forth, you see that that deep distortion is now resolved. And in this case, which is different than the previous one, the distortion happens to be below the channel all the way down. This is just the interplay of the stack response. Sometimes it's below the channel, sometimes it's symmetrically on either side of it. You never know until you see what the stack response gives. Finally, let's have another example. This is one where we have a very, very unusual GeoBody. And this one is where we've picked a 25 by 25 meters and run a tomography with a cell size of 75, 75, 65 meters. So this is courtesy of British Gas. It was a paper published last year, BG. And this is unusual geology. You have a layer of siliceous ooze, so some slimy stuff like toothpaste, and something happens to disturb that layer, and it collapses and squirts this stuff out to the side. So if you look at those two arrows, they're pointing to this area where the ooze has been squirted into, and off to the side is where it used to be. So this stuff has collapsed the layer and gone out over here somewhere, giving a very, very rugose top of that object. As a consequence, when you look below the arrows, you see a dimming. Now, the objective here is not to image that shallow geobody, it's to see deep below it at some of these basalt layers. That's the target level is deeper down. So let's have a look at a zoom in on that thing. So this is what the tomography is able to find with ray-based methods with very high density picking and very small scale length cells in the tomography, and also putting in structural constraints. What we see there is we're able to resolve the velocity differences and the interfaces quite nicely, and that leads us to be able to image the deeper structure. But again, we've got to deal with this before we move on to the deeper imaging. Looking at the gathers coming from there, in the top of the picture there you see the initial gathers, which are all over the place because of ray path distortions, and below them the gathers now mostly flat. Again, not perfect, but good enough to move on to the deeper imaging. And this is what we can sort of get. Now you see there's still dimming there because that's a Q effect, that's an absorption effect. That's not dealt with an acoustic migration. That's a separate issue, that's Q migration. So here we're just looking at the near surface velocity structure, but we're now able to pull out the deep structure of those basalt flows and the sediments below them. And that's the objective here. Another example, this one's from New Zealand waters, a bit further afield. And in this case, again, it's 50-50 picking of the gathers and the tomo cell size 200, 200, 100. So let's have a look here. This is an example of nested near-surface channels. So just underneath the seabed, there are whole families of these channel systems giving rise to deeper distortion. So you can sort of just about make them out there. And you can see in the deep structure, it's not coherent in terms of amplitude. There's dimming in places. So let's have a look at what the high-res tomo can do with that. It pulls out those near-surface channels, which I haven't highlighted yet. But importantly, you now resolve the deep structure, pull out the distortion, and improve the amplitude continuity across those deep events. So it's doing what we expect. And it's that family of channels that's giving rise to that distortion. So resolving those channels helps improve the deep structure. You can't image the deep structure without dealing with that first. Looking at colored velocity models through that, that's the before and after, so 7 iterations on in terms of the velocity detail, and looking at a depth slice through there, you see quite punctual events. So these channels, they're not continuous necessarily. They might be punctual in terms of their velocity distribution and the distortion they cause. Now that was looking at tomography more or less with monoazimuth data. Another very important aspect of this is the illumination of the subsurface. And as we know, the industry has long since moved on to trying to get better and better coverage by looking at different azimuths, either with multi-azimuth shooting or full azimuth coverage with OBC or WAS shooting and so on, which allows us to process with offset vector tiles or some other azimuthal sort order. So let's have a look at a couple of examples of that. So the tomographic engine is still the same, it's just the amount of data we're feeding in has better constraint in terms of azimuthal coverage. So what we're doing here now is illuminating the subsurface from different directions. If you like, in the tomography, that gives us more equations for the same number of unknowns, so we can do a better job of resolving the problem. If we look at gathers from the different azimuths, what you see is you might have the gather flat from one azimuth, but not from the other. In other words, the errors back along different ray paths are seen differently, and that information helps us to update the model more correctly. So here's an example of that. This is the input velocity field, in the middle an update using a single azimuth tomography, and on the side there the MAS is including 3 azimuths in the update. And what you tend to find is you get a simpler model if you bring in more azimuthal information, because the tomography is not struggling to try and find a velocity distribution to explain the data incorrectly. With more data you can do a better job. So a simpler, more geological model is what you hope to get out of it. Now, another aspect I mentioned is representing the move out in the data with a simple curve, that's a parametric picking and a parametric tomography, versus picking the actual detail. So let's have a look at that. So the question there is, what are you inverting against? At the top there we show a gather where we've represented the move out with a simple curve. In other words, we've parameterized the move out. And the same gather is at the bottom there, where we've not put a simple curve in, but actually picked the real move out behavior, which is a little bit of an N shape on that gather. It curls down at near and far offsets. And if we do that, we should be better able to resolve velocity differences. So here's an example of that generalized move out picking. You have very, very strange move out. Some of it's sort of N-shaped, some is a bit like a tick mark. But whatever it is, you can't characterize it with a simple curve. So if we can do that kind of picking, we'll get a better update of the model. So here's some examples there. There's some initial gathers, which are all over the place. They're flapping around because of the velocity anomaly. There's doing second order picking and then tomography. Again, it can't resolve those very strange short wavelength anomalies. And there's trying to do it by calling it anisotropy and picking a fourth order move out trajectory. It looks a bit better, but it's still not right. If we do generalized picking, that's what we get. And comparing that to the correct model migration, it's almost a perfect result. So we do need to resolve those really strange move-out behaviors in order to extract the most from array-based tomography. And that's where the industry has moved today. Looking at the models coming out from that, there's the true model, and this is part of the BP model distributed a few years ago, with some very small punctual anomalies there. So that's the true model. If we remove those anomalies and call that our starting point, so that's what we're going to start with. If you try and update with a second order parametric tomography, that's what you get. So you sort of see where the anomalies were, but it's not good enough. If you go to fourth order, in other words, try and explain it with anisotropy, that's still not good enough. And there's a lot of deep distortion there in the velocity field. Those red colors in the deep are false. Whereas the GMO generalized picking, non-parametric tomography gives that. And if we compare that to the true model, you can see it's doing a very good job. Again, it's not perfect, but this is pushing the limits of ray theory more towards the theoretical limit rather than algorithmic limits. An example of this now, this is ray-based high-res tomo with generalized non-parametric picking on a 25-75 grid, cell size 200, 200, 100 in the tomography. So there's the gathers coming out from the starting model. After generalized picking with 5 iterations and parametric picking with 15 iterations. Now the results are more or less the same here. We have sort of converged after a lot of iterations of conventional parametric tomo. So another point here is we should be able to converge more rapidly with the generalized move-out picker. And looking at the models coming out from that, that's the detail we get after 5 iterations of generalized move-out picking versus 15 iterations of parametric. So sometimes you can get to the same place, sometimes you can see through the complexity, but it might take a lot longer. So it's an important point. Moving on now to more contemporary methods, namely waveform inversion. So again, remember in that little matrix of possibilities, we have 2 types of data, raw data or migrated data, and we have 2 types of theory, ray theory and waveform theory. So we're now going to have a look at waveform inversion. So that's dealing with wave theory on the raw data. Again, you can write the waveform methods on migrated data, and some people refer to that as wave equation migration velocity analysis. And you'll also see some people mixing the two so that each method constrains each other. Costs a lot more, but it might converge more rapidly. Again, the idea there is to set up a tomographic solution which is more or less the same as with ray theory, but the thing we're trying to minimize now, that residual, is the difference between the model data and the observed data, not just the travel times. But to do that correctly, there's a lot of things you've got to take into account, namely everything which affects amplitudes, and that involves elastic propagation, things like Q and anisotropy. There's a whole bunch of things you ideally should take account of in your forward modeling and your inversion. But we're not there yet in terms of state of the art, but give us a few years, we might get there. So an example, this one courtesy of BP, it's the well-known Valhall case study. There's a migration using a model based on ray tomography and the corresponding migration based on waveform tomography. And it's difficult to tell whether one is good, bad or indifferent compared to the other, but what you do see in the deep part of the section here with the model from waveform tomography is a more continuous deep structure. So that simpler deep structure implies that the velocity model above it is more correct. If you look again at the ray-based model, that deep event falls apart. It's a poor image in the deep section, so something's wrong in the overburden. Looking at depth slices through there, in the shallow, all you see in the migration result is the imprint of the OBC acquisition layout. whereas for the same depth slice through the waveform inversion velocity model, you see a lot of detail. This picture also points to perhaps the future of waveform inversion, which is to supplant migration as the tool on which you interpret, and give you the possibility of maybe interpreting directly on the parameters coming out from the inversion. That'll take a while yet, because that would require full elastic, anisotropic, viscoacoustic or viscoelastic waveform inversion. So a bit down the road for that one, but it's a possibility. That's the promise for the future. Going a bit deeper, this is a slice through the model with ray theory and a slice through the model with wave theory. So a lot of detail in the wave theory tomography. And deeper down again at about 1 kilometer, this is now down the target level. That's a slice through the velocity model from ray theory and wave theory. So the amount of detail in the wave theory model is enormous. And if you look at some of those very small faults, like the one going almost vertically there, they're looking at a scale length of maybe about 100 meters. So very, very fine resolution in the parameter field. That's not the migration we're looking at. That's the velocity field coming out from the inversion. So to conclude, the near surface is the biggest problem we faced in most imaging projects. If it's a land environment, that includes the topography and the weathered zone and things going on. In a marine environment, the very near surface is simple, it's water, even though there might be an unusual water velocity profile. But the problem really comes in the marine environment just below the seabed. Paleo channels, infills, hydrates, whatever it is, something that distorts the downgoing wave field. We have to deal with it in order to build an acceptable model of the subsurface. So the near surface is key. You have to get it right first. So that's all for today, folks, and thank you for your attention.